what we do at the very high end, how it's related to technology leadership and the human assets that provide global leadership.
I thought what was so interesting, and again, confirm or deny if I have this correct, but there's a gap between the market opportunity versus everything that goes into making systems for that market.
You could see it even then that the cost to innovate was rising.
The bet, maybe the implied bet, was that over time, those players would come to see the wisdom of focusing on HPC, and that in fact happened.
From Orion X in association with Inside HPC, this is the At HPC podcast. Join Shaheen Khan and Doug Black as they discuss supercomputing technologies and the applications, markets, and policies that shape them. Thank you for being with us.
Hi, everyone. It's Doug Black again. I'm here with Shaheen Khan of OrionX.net. Shaheen, great to be with you. And we have a great special guest for our At HPC podcast this week. Dan Reed, he's presidential professor at the University of Utah and a HPC luminary and thought leader. Dan, it's great to be with you.
Delighted to be here, Doug.
So Shaheen and I have both read your article on American competitiveness, IT and HPC futures. Follow the money and the talent. So it's kind of a survey piece, an insight piece on the challenges facing the HPC industry. The focus in particular is at the very high end of supercomputing. Is that correct?
That's right. I mean, the commodity elements of HPC, I think, are tracking just fine. They're the trailing leaders of exploiting what's widespread technology. This piece is really focused on the bleeding edge, what we do at the very high end, how it's related to technology leadership and the human assets that provide global leadership.
Then you also had an archive paper that you wrote with Dennis and Jack, reinventing HPC challenges and opportunities. How different is that paper from this one?
So when I wrote the piece on my blog, I circulated it to some friends and welcomed some feedback, and I incorporated some of that feedback into the drafts. And then as I started to talk to Dennis Gannon and Jack Dungara, one of the things that we thought we would do is we would try to tighten the focus of the article. And so what's on xArchive focuses more narrowly on HPC futures, omits discussion of some of the U.S. talent and educational competitiveness, and really tries to take a crisper focus on really what I think is the forcing function for the future of HPC, this combination of the rise of massive cloud services on the one hand, and how that's shifting the locus of innovation, the end of Dennard scaling and Moore's law, and the whole sets of issues that Intel is struggling with relative to TSMC and semiconductor leadership. And then how we put those pieces together and think about how we go forward as the cost of innovation at the bleeding edge. I wouldn't say it's become prohibitive, but it's become a very expensive game to play. And it's priced some countries out of the market. And so how we think about new innovation around chiplets in this brave new world was really what the xArchive tried to focus on a little more narrowly.
I thought what was so interesting, and again, confirm or deny if I have this correct, but there's a gap or a disconnect, you seem to be saying, between the market opportunity, the straight up business market opportunity at high-end supercomputing versus everything that goes into making systems for that market. It's so expensive. The skill level is so high. I guess the opportunity cost is so high that fewer and fewer companies really are willing to compete in that area.
Yeah, I mean, I can tell you that when the Exascale ECP initiative was being debated, I was part of one of the Department of Energy panels. There were many assembled to talk about this, and I was reflecting on this in a discussion with some folks last week. We had a long debate about whether Exascale, as it eventually unfolded, was the right thing to do or not. In other words, there one more turn of the crank in silicon technology, or was it time to make a massive bet on quantum or some other alternative? And we didn't think those were ready for prime time, and I think time has proven that that judgment was correct, even though a lot of progress has been made on quantum. But it was clear that we were facing an inflection point. You could see it even then, that the cost to innovate was rising, and we can see that in the top 500 list. The machines are getting bigger faster than semiconductor improvements by themselves would lead. We need bigger and bigger machines, not just better technology to get higher performance, and that means they get more and more expensive. So yeah, there was an economic piece, and then it was convolved with the technology questions, and as you said, the shifting nature of the market, the fact that the locus of financial control and innovation has shifted away from what were maybe the traditional vendors to a new set of vendors who have a different set of market objectives. And so, put it another way, the big cloud vendors, they are driving revenue to scale and have market capitalizations that dwarf what we see of the traditional semiconductor and computer vendors. And so they're building custom systems themselves, and the traditional players are often more likely to be supplicants or smaller players than the drivers of that innovation. So some of the question is, how do we recognize a reality and adapt to it?
Dan, if we focus on that, and Doug, please bring us back if I broke your thread. We did already this one time when we had the big vector supercomputers, more or less specialized systems, and then massively parallel, and then clusters. And then suddenly we figured that strapping together a bunch of PCs could really get us there. And I remember back then sort of jumping up and down and saying that, look, but you guys are getting rid of, you guys as a collective community, we're all as a community are really getting rid of the specialists focused on HPC vendors in favor of those who are doing HPC by accident. And I think the bet, maybe the implied bet, was that over time, those players would come to see the wisdom of focusing on HPC. And that in fact happened. So people like Intel and Samsung and all these other PC manufacturing oriented vendors over time moved to servers and then moved to HPC. And we are where we are now. Are we betting that the same thing is going to happen this time around? That the people who come in entirely motivated by the consumer market and to some extent by AI are going to morph into an HPC oriented thing? Or are we thinking that HPC is moving in that direction itself?
I think it's some of both. Certainly, you're absolutely right. Commodity clusters, and the attack of the killer micros really disrupted the ecosystem. And all of us lived through that and saw that change. And it was the old guard and new guard. Believe it or not, in the late 70s, early 80s, I had this crazy idea that we'd build supercomputers out of microprocessors. And that was pre-83, 86. That was a crazy idea back then. But, that's become mainstream. We rode those performance increases. We took advantage of graphics accelerators. And what I really think is there's another kind of commodity inflection point happening. We tend to, history doesn't repeat itself, but they say it rhymes. And I think there's an element of that happening. We're seeing the HPC needs of high-end AI driving the cloud service providers and the hardware vendors to look at how to accelerate those workloads. We have seen HPC adopt AI, and there was a time a few years ago when I think the prevailing wisdom was that AI and HPC was evil, and now it has become largely mainstream because it's let us accelerate inner loops and build all kinds of parameter space explorations that weren't possible with traditional HPC approaches. So I think some of it is the pull of AI HPC in the cloud space, and some of it is the push of this different kind of technology price point.
So I don't know if this is a little off track, but in reading the piece, and again, this disconnect between business opportunity and cost opportunity, the cost of building these systems for a relatively small market, is it fair to say maybe the Chinese economic model, a command economy, in a way, it could be a big advantage for them in the realm of high-end supercomputing? They could simply have these systems built without worrying as much about a market for them.
So this is where, to go back to where we started, I would distinguish the high-end bleeding edge from the mainstream of commercially viable HPC, because we know that market is growing. I think at the really high end, we have been blessed, if you will, in living in an ecosystem where what in other science domains would have been government-funded, purpose-built scientific instruments actually had a commercial market, maybe a subsidized market, but nevertheless a commercial market. If you're building an extremely large telescope, you don't go out to the vendor of telescopes and buy one. It's a bespoke instrument, and it requires government investment. We do it because we want to explore some frontiers of knowledge. We may do it because there are national security reasons, but there are compelling reasons beyond economic to build those things. And one of the questions that I don't know the answer to is whether at the truly high end, given these cost points, we may be at that point of really thinking about more of our bleeding edge HPC systems as being bespoke scientific instruments, that we understand we have to subsidize the NRE and the capital required to build them, that the market itself cannot sustain them. And again, I would distinguish what I would say is the commercially viable part of HPC, the mid-range where people buy clusters all the time and that market's growing, to the really leading edge where you're talking top 10 of the top 500, say.
As I recall, there were two primary answers to these problems. One could be that maybe high-end supercomputing could move toward the technology offerings of the big cloud players. And secondly, obviously, more government funding for these bespoke systems. Is that the two solution tracks you're looking at?
Those are two of them. I think the one that we haven't touched on, and I'll hark back to something that was said a moment ago about when clusters and the attack of the killer micros appeared. And I tried to make this point a little bit in the blog, but we expanded upon it in the X-Archive paper. In the 80s and 90s, there were a wide range of really interesting prototyping projects taking place around the world. New architectural ideas were being explored, software approaches and systems were being built at fairly substantial scale to test those ideas. The Cosmic Cube was really the birth of what became a lot of message passing machines, and that was a Caltech research project. I was at Illinois when the Cedar SMP system was being designed and built, and John Hennessy at Stanford was working on Dash, again, a shared memory cache coherent SMP. There were a lot of those kinds of startups and research projects, some because the federal government invested in those startups. DARPA put a ton of money into those projects, and academia did as well. What I'm really trying to say is we had a whole explosion of exploration. We're largely in a monoculture now, x86 and accelerators, and there's some variants to that, but the first order, that's what we have. How do we get out of that? And I don't want to say evolutionary dead end, but out of that monoculture to explore a wide range of ideas. I think that's the third piece. And that's why I talked about building some prototypes at scale and testing ideas, because that's the other way that you hang on to talent, and not just application developers, people who think about system software, packaging, cooling, all the other things that go into building systems. They want to be part of something, and the opportunity to build something new can be an educational attractor, both in the university and national labs, but it's also the thing that motivates people in startup companies. And so how we think about trying to get that pizzazz back, I think, is the third piece of the question. And that was kind of the way I was trying to segue in the conversation about chiplets and innovative system design. That is one of the opportunities that I think we now have, because Moore's Law, nobody could keep up with Moore's Law. You built a parallel system, 18 months, you were run over by technology. We're not in that space anymore. And so chiplets give startups an opportunity to mix and match technologies, leverage some mature products, but innovate in some spaces. And maybe we can find a new way forward in that. That's, to me, is one of the opening and interesting questions.
As an observer of the industry, I see that the industry chases price performance at all costs. Technical debt be damned, it's no problem. I'm going to go for what is price performance now. And if I have a problem 20 years from now because of what I did, no worries. I'll figure it out when I get there. And I feel that's exactly what we did. We chased price performance. The whole consumer market PC industry was where that was at. So we gravitated towards that. And of course, killer micros are no different than solid state memory. It was just new technology that we were going to take advantage of. And we figured out how to do that. And now that that party is over, that's definitely a phase shift. But then that goes, in some ways, whatever the best price performance is going to win. And are these chiplets and custom systems and bespoke systems going to deliver that? Now that goes against the workflow part of this that says that, okay, you might really do well here, but you may not do well there. And that sort of tempers the special purposeness of this stuff towards more general purpose. And Fugaku is a really good example of that. How do we square that whole thing?
Well, I think, the Japanese machine is an interesting case of actually trying to split the difference because it certainly has some bespoke elements based on workload analysis. And if you talk to Satoshi about their future thoughts, they are looking again at what kinds of workloads they can carry forward with next generation designs. The ugly little secret that we don't like to talk about is that for complex multidisciplinary applications, we're getting single-digit percentages of peak hardware performance on those commodity microprocessors. So we don't like to admit that, but we do, and that is the consequence of following that path in some sense. And yes, you can get kernels faster, and yes, if you work hard and optimize for GPUs and manage data placement, you can improve performance. But for complex applications, it's really hard.
Yeah, I remember, I think was it David Cook who said, it's not the maximum performance, it's the minimum performance.
Yeah.
that is important. And minimum performance is like 3% sometimes, yes.
But, that tension between general purpose and special purpose has always been there. And it kind of comes down to how important your application is. I look at Anton as a really great example of a purpose-built machine to optimize for what's effectively quantum chemistry. If the application is important enough, you can do it. But I also find it interesting that the science breakthrough of the year in 2021 was the AI-driven protein folding. And our sort of traditional algorithmic approaches to protein folding, we've been struggling with that problem for 20 years. We've been making incremental progress, but really incremental progress. And this was a completely different kind of take that speaks to, I think, the other thing that I try to gently say is, and I come from this background, the PDEs dominate the world and we build machines to solve those. And there are a huge set of our science problems like that. But there are other problems not like that, that are really core to scientific discovery. And so that speaks also, I think, to the population of people and that other rich and fertile intersection of new ideas and technology as well.
Your comments about co-design, maybe looking at co-design writ large, that I've always found one encouraging factor in all this is that funding for the Department of Energy is a rare area of political consensus coming out of Washington. So maybe there's grounds for hope that the country will get increasingly behind these ideas that you're talking about.
Well, I co-chaired with a couple other people one of the DOE basic research needs workshops 3 years ago, looking at co-design. And this sort of speaks to what you were saying a moment ago about mapping algorithms to architectures. Whenever you insist on compatibility, you're drawing a layer and you're saying, okay, you can co-design below that, but above that, you have to maintain consistency. That really hamstrings you in many ways. And so part of what we were pushing in that basic research needs workshop was to start from device physics up and look end to end, rather than, for example, saying, okay, it's got to have x86 compatibility. You can innovate as long as you do that. That's a pretty big constraint. And the reason I was throwing out the chiplet idea is I think that might be a place where there's a happy medium, because you can dial that knob between essentially complete compatibility to radical alternatives and explore that space for different suites of applications. And there's a lot of ferment in that space in the AI hardware startup space right now. Some places I think that there may be some innovations appear, but the highest level, what I was trying to say is we need to explore a bunch of new ideas, and we need an ecosystem that encourages that to happen. And then a variety of forces will shake out what are the best of those.
Your archive paper had 6 maxims that you articulated at the end. Would you mind taking us through it?
Well, let me pull up the list here and make sure I get them in order.
It started with the semiconductors.
Yeah, semiconductor constraints dictate new approaches. And this is really the end of Moore's law and end of Dennard scaling, but more importantly, trying to make the point that cost per transistor is actually going up as we get closer and closer to 1 nanometer. And so the traditional notion of we'll just cram more onto a chip, that's got to be the best alternative, is increasingly less so. And that means we need to think about how we mix and match and package. It also has some geopolitical implications about semiconductor processes. And, Gelsinger has spoken eloquently about what he's trying to do. Intel and the CHIPS Act discussions are all part of that. And at the risk of sounding a little political, watching what's happened in Ukraine and thinking about Taiwan and China and TSMC, there are some global implications potentially there. So how to balance the semiconductor constraints is the first one. The second one is really what we were just touching on, encouraging some end-to-end hardware co-design where we play with ideas and think about how to optimize hardware given algorithmic implications. We see that happening in the cloud space. Cloud vendors are doing purpose-built designs of Gravitons at Amazon, the TPUs at Google are examples of that. The third one was prototyping at scale. Take some of those ideas and try to explore them in the hardware software ecosystem. The fourth one is something we also touched on, that the HPC ecosystem is bigger than PDE solvers, that it will always include those, and don't misunderstand, but it is bigger than that. And how we think about embracing that, and AI is an example of that. The fifth one was that cloud economics have changed the supply chain ecosystem. And one of the things that was in the blog is also in the X-Archive article is if you take pretty much everybody you think of as a computing vendor, with the possible exception of NVIDIA, and you sum their market cap, it's less than the market cap of one of the cloud providers. And so when you're spending money at that scale to build out cloud services, data centers, and hardware, you've changed who's driving the locus of innovation. It's not good or bad, it just is. And you need to think about what that means. So another way to say it is, if you're a chip vendor, you follow the money. And where's the money? It's in that space. It's not in HPC. Well, it is some in HPC, but much more of it is over there. And I think one of the things that we struggle with, and I told an anecdote about when I was at Microsoft trying to convince Steve Ballmer to do something in the HPC space. And he said, yeah, we could make money there, but we can make more money doing something else.
Right.
And that has always been part of our challenge. The old saw about a way to make a small fortune in HPC, start with a large fortune and ship a generation or two. It's been proven sadly more than once. And so that gets to that tension of government investment versus whether capital markets will work. And it's probably neither one nor the other.
I had a
All
sixth
right.
one in the archive paper, and that was the societal implications of technical issues really matter.
That's right. Really a point I tried to make in the plenary panel at SC21 about ethics, which is that we in computing and HPC in particular, we underpin a big chunk of what our society does, not just the science and engineering pieces, but the way advanced computing is used almost everywhere. And we need to think about the social responsibility that goes with that in the same way that other domains have embraced that, right? So as much as we want to be geeks, we actually do have an effect on our society, and that's a responsibility.
So one of the reasons I was focusing on this one, and also the HPC is a lot more than PDEs, as much as I am a big advocate of everything is ultimately a PDE and a graph, is that
Jack Nagar would say it's a linear system when it does work.
it's a linearizable system. It begs the question of what is HPC and how is HPC evolving? And is it the rest of the world that is finished solving the easy problems and is now grappling with HPC problems because that's what's left? Or is it that HPC is diluting itself, for lack of a better word, to cover areas that are outside of traditional HPC? And AI really brings that into focus. Is AI an aspect of HPC because it's all deep learning and it's matrix multiplies and PDEs and backpropagation? Or is it that it's a net new tool that is pulling HPC into a new direction? And how do you see all of that?
It's probably all of those. You know, my friends in AI used to joke that every time we figure out how to do something, people say that's not AI. And so by definition, AI is the stuff we don't know how to do. And, you know, clearly deep learning at scale has been a revolution. And I'm old enough to live through a couple of AI winters where there was the boom and the bust. And there probably will be another one, but I think we're at a higher plane and I don't think it's going to go back to where it was. Clearly, let me say it in a negative way. Think about where HPC would be today if GPU accelerators and deep AI had not appeared. We'd probably be in a world of hurt.
Yeah.
because those two things created an incentive for investment in hardware that we could use. Some by modifying algorithms, some by influencing the evolution of hardware. I mean, NVIDIA has been trying to navigate that sweet spot between both. But you might also ask, if Bitcoin mining hadn't been such a big deal, how many GPUs would NVIDIA have sold? So there are multiple markets there. I think it's probably some of both. We've broadened our space of including AI in lots of algorithmic approaches that a few years ago we would not have. But we've also helped shape some of the AI hardware space. And I think the large-scale cloud providers have learned some things from HPC about low latency communication and system jitter, all kinds of technical issues at scale. It's gone the other way too. I mean, a lot of the innovation in energy efficient data center design that was driven by the hyperscalers has come back into high-end HPC to drive energy efficiency. So there's been some crosstalk there. The place that I think we've seen less uptake is the cloud software ecosystem and the HPC software ecosystem are still largely disjoint. And Jack and I wrote an article about that like half a dozen years ago as well. I still think there's more opportunity for fertile cross-fertilization between those two.
Doug, if you don't have another question on HPC, I want to ask you, Dan, about quantum computing. We mentioned it in passing. What is your current perspective on that as the promise and the complexities that it presents?
Well, I ran Microsoft's quantum computing project for a while when I was at Microsoft, and I'm no quantum computing expert, so let me qualify everything I'm about to say with that. I think we've got a long way to go to build stable, logical qubits. And so when people talk about the qubits that are out there, they're really mostly talking about the relatively unreliable bare hardware qubits. I've been told it might take as many as 1,000 hardware qubits to build one really stable, logical qubit. So if you think about that, we're a long way from building a large-scale quantum machine. Progress is clearly being made. My guess is that even when successful, quantum is likely to be a special purpose accelerator. We have also struggled on the algorithmic front to think about how to express problems in quantum terms. And so there's some different research and education issues there. So my guess is we will succeed, I hope, in a way more positive than the old joke about gallium arsenide always being the technology of the future. But I think quantum is likely to be a special purpose and accelerator. It's hard for me to see it being a general purpose replacement. I could be wrong, but that's my 2 cents.
Yeah. I heard this said about autonomous vehicles that for a good while it was always 10 years away. And for the past 15 years, it's now 5 years away. So it's made progress.
Yeah, it is interesting how we have different expectations on that front. I was kidding someone the other day that this was about explainable AI and a lot of the questions about the ethics of autonomous vehicles. And I said, we don't understand how humans learn how to drive either. We've made an uneasy peace with that. And so you do sort of have to think about what symmetry in terms of your expectations are.
I was going to say, there's that old question. If we knew when cars were being invented or becoming commercially viable, that this was something that would provide tremendous convenience and importance to people's lives, but would cost 30,000 lives a year, would we have done it? So.
Right. Well, that's the whole societal implications that you had as a maxim. It's a huge one.
Yes, that notion of turning people with still maturing loose with a lethal vehicle would be hard to reconcile.
That was a great discussion, Dan. Thanks so much. In the little blurb that I write introducing this episode of the podcast, I'll include links to your pieces. I think it's a great contribution. Thanks so much.
And very timely indeed. Thank you.
Well, thank you. The goal was to start a discussion because I do believe we need to talk about these issues. I'm not sure I know the answers. I'm not even sure I know all the questions, but I think I know some of the questions. And that's the place to start.
Thanks so much.
My pleasure.
That's it for this episode of the At HPC podcast. Every episode is featured on InsideHPC.com and posted on OrionX.net. Use the comment section or tweet us with any questions or to propose topics of discussion. If you like the show, rate and review it on Apple Podcasts or wherever you listen. The At HPC podcast is a production of OrionX in association with Inside HPC. Thank you for listening.